from CMU. So Shubham is an assistant professor in the Robotics Institute. And before coming to CMU, Shubham was at Berkeley doing his PhD with Jitendra Malik. So Shubham has done a lot of work on 3D and has engaged in many debates about how 3D fits into manipulation and robotics. I guess Shubham has some very exciting work which he is going to talk to us about today. So Shubham, really looking forward to hearing all your perspectives on 3D. Now, before I hand it over to Shubham, let's also thank Tao for organizing this talk and inviting Shubham. With that, Shubham, please take it away.
Thanks, Pulkit, for the introduction, and thanks again, Tao, for organizing everything. And I guess before I start, I'm happy to keep this informal, so feel free to ask any questions, and I'll try to leave a bit of time at the end for more philosophical debates that I'm sure we'll get into. But yeah, I think getting started today, I want to talk about this task of being able to reconstruct sort of generic objects in a couple of settings that we consider, both isolated and handheld ones. But before going into details of this, just to set this. Sorry, was there any question? Before getting into details, just to set the stage, right? So if we as humans or a robot sees an image like this, this image is actually just a 2D representation that essentially is one particular perspective of the underlying physical and spatial reality, right? That this 2D image that we are seeing is essentially just a painting that is depicting something about the underlying spatial physical world. And if, for instance, you are an agent or you're interested in building a robot that is seeing this image and then wants to act in the world, in some sense, you don't really care about this 2D representation. You care about this underlying physical world that you must eventually act in. For example, if you want to lift the cup and maybe move it to the kitchen somewhere, you need to understand how far away that cup is, how big it roughly is, what its shape is so that you can go around and grab it. Or if you want to perhaps move some furniture in the scene, walk around again, you need some spatial understanding of where the free space is, how big the furniture items are, and perhaps what are good points to push them around and so on. So with this in mind, that even though we see images, we are essentially interested in acting in and perhaps representing the physical world underneath them. One task that I've been looking at for several years is that of being able to go from an image or a small set of images to construct some 3D representation of the underlying world. And when I sort of talk of this goal or this objective of being able to build 3D representations, if some of you are only sort of cursorily familiar with the areas of vision, you might just be wondering, why is this a challenge? Haven't we sort of solved 3D reconstruction a few years back? For example, this very famous work from Noah Snavely's group, a group from UW where Noah was, I think at that time, a postdoc, allowed us to reconstruct entire cities or entire monuments given several images just taken from the internet. For example, taking thousands of images of the Colosseum, one could obtain a very accurate and detailed 3D model of the Colosseum and even figure out where each of the images were taken from. And similarly, of course, this technique was not limited to just one specific scene, but could let us reconstruct a lot of monuments from just web data and even cities in some case, for example, being able to reconstruct Rome. And similar techniques have allowed us to reconstruct other things. For example, this sort of very famous statue reconstruction example, given a few depth images, we can get very precise measurements of the 3D structure of this underlying object. And these techniques have, of course, been used to reconstruct other things of interest. For example, sitting presidents, where given this scanning setup that you saw, we could get a very detailed, I think, in sort of an official 3D portrait of a sitting president. And while we have made a lot of progress in being able to very accurately reconstruct these different things that I showed, sort of statues, faces, and cities, one axis that I would like us all to think about is this axis of ease of inference. And in context of this axis and one other axis, just think about the landscape of being able to reconstruct 3D from images. Now, all the examples that we were seeing earlier were, in some sense, more to the left of this axis, which is if you want to reconstruct the single instance or a single scene or a single object, you need to put in a lot of effort. You need to take either thousands of images of this one specific object or perhaps hundreds of images these days, or in this particular case, build this custom scanning setup that would, in which you would situate this one new object and then obtain a scan of it. And on sort of the other extreme of this axis, which is where we'll focus a bit more in the talk, is just something that's much easier to do. For instance, if you just take a single image of a new scene, or if a robot just enters a new house, observes it from one perspective, if given just this very limited amount that is arguably much easier to acquire, we also want to be able to reconstruct 3D from images. And all the approaches that we were seeing earlier were somehow more towards the left of this axis, and in this talk, we'll try to move towards the right of this axis. However, just considering this axis on its own is not sufficient. We might have systems that can very accurately reconstruct faces from just a single image, but maybe these systems are not very broadly applicable. And so a complementary axis that we should also strive to make progress on is that of generality, which is, there are arguably tens of thousands of object categories that exist in the world. And one question that we must ask for any approach that we are looking at is, if we just download the system that is there, how many amongst these 10K categories can you reconstruct given the code base? And again, as I said, to sort of the upper end of this axis are some systems that we have built over the years in 3D reconstruction, things like SFMs or SLAM systems, which really work very well in generic scenarios, but as we said, are a bit hard to use for new instances. And perhaps the bottom end of this axis are systems that are really specialized towards, let's say, just one category. For instance, if we have a face reconstruction system, it might do a very good job at being able to infer 3D structure of faces, but that system on its own is not something that will be generally applicable towards the thousands of different objects that one might encounter across our daily lives. And with these two sort of axes in mind, I want to paint you a brief picture of what I see the current landscape of 3D reconstruction approaches, and in that context, present a few of our latest works. And in particular, the classical multi-view approaches that we have looked at sort of very firmly lie in the top left corner. The really general approaches make very few assumptions for the structure of the scene, but of course require you to take many images of the order of hundreds or thousands to be able to reconstruct the novel instance that you're interested in some detail. And there have been modern versions of these approaches, or modern approaches that tackle similar settings. For example, you may be familiar with works like neural radiance fields, which can give us very precise and high quality reconstructions and view synthesis, but again require sort of an order of 50 to 100 images, to say the least, to be able to capture this hemispherical 3D structure. And some approaches have looked at relaxing some assumptions in nerve-like approaches, for example, being able to work with fewer images or being able to work with approximate camera viewpoints. But again, all of these approaches, I'd argue, fall towards somewhere on the top left of the spectrum, where again, very general approaches that can reconstruct arbitrary things, but sort of a bit difficult to use for a new instance that you're interested in, because you would again require many images and perhaps precisely calibrated cameras as well. And on the other end of the spectrum, in the computer vision community, we have been making progress on systems that infer 3D, perhaps in a much more easier way given a new instance. For example, given just one image of an object, such as a car or a bed, we've been building systems. I think these are works from sort of the decade 2000s of decades, where we've been building systems that can understand 3D from just this one image, and more recently, CNN-based systems, which can also perhaps infer 3D a bit more accurately. But unfortunately, all of these systems are very limited in their generality. I think at best, they can reconstruct something around tens of objects categories, or perhaps on a good day, some of these systems can handle about 20 object categories, but we are very, very limited in terms of the class of objects that we can understand given just a single image. And of course, once we set up these two axes, the ideal system that one would want to build is something that is towards the far right, a system that is very general, can reconstruct novel objects that you see from just a single image, and can do this across a very broad set of objects, perhaps all the 10,000 objects that I was talking about earlier. And we have striven to make some progress towards this goal from both ends. In particular, one work that I'll not be able to talk about today, but I would encourage you to look at if you're interested, tries to relax the assumptions that we need to reconstruct sort of an instance given multi-view data. In particular, we show that given a much smaller number of images, for example, just 8 images of an object, we are able to infer its 3D structure, even given just approximate cameras. But what I want to focus on today is sort of making progress on the far right of this plot, where we'll be looking at single view prediction, and in particular, looking at how we can build systems that scalably, that are scalable to hundreds of categories, if not thousands. And in particular, I want to talk about this upcoming CVPR paper, which is in collaboration with Kalyan and Facebook and Abhinav at CMU and Facebook, where we were looking at what it takes to build 3D reconstruction systems that can handle, in the limit, something around thousands of object categories. And to be able to do this, one question that we ask is, why is pushing generality, or why is scaling systems that can infer 3D for generic objects really hard? In particular, this is in stark contrast to 2D inference, where we have systems and data sets such as this. For instance, this image is taken from the Elvis data set, where we can very reliably segment out just generic objects. And I think this is an annotated image, but the state-of-the-art systems that we have trained on this data are also perhaps not too far from being able to give predictions like these. But given just a generic 2D image, they are very good at being able to identify generic objects and being able to even demarcate the boundaries of this. So we have made significant progress in pushing the generality of these 2D recognition and 2D segmentation systems. And why is it much more hard to do this for being able to understand all of these objects in 3D? And I'd argue that one of the main bottlenecks is that the traditional way that we have for machine learning requires these annotated pairs. So for each image, we would require an annotated 3D structure. And if we follow that paradigm, it's much harder to scale because 3D annotation is just much more expensive. For instance, this is a particular 3D data set that was collected by Stanford in 2014, where we are visualizing the annotation process for a single instance. And the way this annotation process works is, given an image, a user would select a template from, let's say, 1 out of 6 cars, and then sort of very carefully try to align that template given the image that they're seeing. And per instance, it might take of the order of perhaps a minute. But even more fundamentally, this annotation is just approximate. We have only sort of 6 cars available from which to choose. And if you think of more complicated categories such as bagels and chairs and perhaps vacuum cleaners, it's just much harder for this approach to even be applicable to those scenarios. In contrast, 2D annotation is just much faster. And this is, of course, a reason why we have 2D recognition systems that work across many, many generic categories, because the 2D detection systems only need to rely on annotations of this form. And in our work, we've been looking at basically using this more scalable data of 2D annotations and asking whether we can learn 3D from it. So just as another example, this is, again, we have widely available recognition data sets. For example, this is a GIF from the Open Images dataset, where you can very easily get segmentations for categories like eagles and faucets and sort of other categories like teddy bears, etc. And being these 2D annotations of segmentations and bounding boxes are just much more easily available and are arguably a much more scalable data source than having to rely on 3D prediction. And so sort of one solution to be able to build 3D prediction systems that scale to generic categories is to reduce our reliance on 3D data and instead see if we can learn from just 2D data instead. And this, of course, our work that I'm going to talk about today is not the first one to present this idea. Several previous approaches have looked at what is called this unsupervised 3D learning, though in quotes, because we are using some sort of supervision, so I don't quite agree with the term, but sort of pedantics aside, a common setup that approaches that want to scale 3D prediction have studied is relying on these 2D image collections. In particular, we have many 2D images of a particular category, such as birds, and for each instance, we additionally have something like a foreground segmentation mask available. And given just this, the work that I'm going to talk about and several prior approaches have looked at being able to learn 3D. Now, unfortunately, most prior approaches, including some work from our group, make some very limiting assumptions to be able to train using this data. In particular, one very popular assumption is that the category that we are considering is only allowed to vary in a very constrained linear deformable way. Perhaps we are learning a morphable model across the category or are limiting articulation in a certain way, but we make an assumption that all instances that we see lie in a very linear shape manifold. And while this works very well for objects like horses and birds, this is again a rather limiting assumption for generic objects. Perhaps if we think of categories like chairs, where the structure can vary a lot, or categories like vacuum cleaners, where things are very reconfigurable. One slightly more general assumption that sort of a general prior that people have used to, again, get around to being able to use this sort of data is, instead of enforcing a constrained deformation prior, enforce something like an adversarial constraint that the 3D structure we infer should look realistic from other viewpoints. And in principle, this is a much more sort of general prior to use and is arguably more applicable across broad categories. It's just unfortunately much more difficult to tune, and as I'll show later, leads to systems that are a bit hard to train and don't perform as well. Now, the reason we need either of these priors is being able to learn 3D prediction from these segmented image collections is rather ill-posed. For example, one trivial solution that a system might learn is that everything is just a very flat cardboard-like structure and there's no depth to it. And it could just explain all the data that it's seeing by these sort of flat cardboard-like bird predictions. And all of these priors help us prevent some of these degenerate solutions. And the reason why we need some of these priors in all these previous approaches is that they learn 3D prediction given this segmented image collection in a category specific way. For example, given just 600 images of birds, we learn a neural network from scratch that is trying to understand the 3D structure of birds. And because we are learning this neural network from scratch, these degenerate solutions that I mentioned, something like a flat bird, are much more likely, and we need regularizers like the ones mentioned in the previous slide to prevent these. And sort of all these priors, as we argued, limit either the applicability of these methods to generic categories or are just much harder to tune and make them work very well and sort of limit the performance, again, for generic objects. And in our work, we were just taking a look at this assumption of being able to, of training networks in a category specific way. In particular, if we want to train a model for birds, we would take 600 images of birds and train this network on them. If we wanted to train a model for cars, we would take another 1,000 images of cars with segmentation masks and train a different model on them, and so on for each category. If we are interested in training models for thousands of categories, the conventional approach for learning from segmented image collections is to take n images for that category and train a model from scratch for that category using some of these priors. And so in our work, we just wanted to look at this assumption a bit more closely and instead suggest an alternative where instead of training sort of models from scratch on new categories, we would, one, pre-train these models using synthetic data. So, while for new categories that we would be interested in, such as kangaroos or hats or bagels, we might not have a lot of 3D models, but we do have 3D data existing for certain other categories. For example, indoor furniture-like categories or things like cars and airplanes, where people have created synthetic models which have some reasonable texture. And so if we can pre-train on them and then self-train on these category-level image collections, that, as I'll show, sort of simplifies the self-training process and lets us train predictors that are much more robust. And then instead of eventually having just a single, eventually having these thousands of per category models, we'll basically show that distilling them into this common model that can predict 3D structure across generic objects has a lot of benefits. In particular, it can learn from the common structure across categories and improve performance on seed categories. And even because it is trained on a very broad set of objects, even allow sort of zero-shot prediction on things that hasn't been seen before. And so this is sort of the overall approach, and the specifics are actually perhaps the simplest instantiations of this. And the particular model that we were using, you can think of it as an encoder-decoder network where, given an image, and I apologize, this is it should actually be a segmented image. So we were taking an image where only the foreground pixels are colored and the background pixels are white. So given a segmented image, we have an encoder that maps this image to a high dimensional latent vector. And this latent vector then just conditions something like an implicit coordinate-based network, where this coordinate-based network is taking a particular point X and inferring its density, which is some representation of geometry, and the color associated with that point. And in particular, the architecture is inspired by the paper cited below, and I encourage you to read that for more details, except in our work, we were using it in a more conditional inference setting. And given this network, it's sort of equally implying an implicit 3D representation for the object. Sort of given a particular Z, we can obtain a sigma and C for any query X. And so a particular prediction of a Z is equivalent to having this implicit 3D representation for a particular instance. And this model that I'm showing here, we first just pre-train it on a lot of synthetic data. In particular, we use the ShapeNet dataset, and using over 40,000 objects rendered from multiple viewpoints, we simply train this network using multi-view rendering losses. So given one image of this object, we predict a Z vector, and given a novel view of the same object, for instance, the chair now viewed from slightly top, we just say that the rendering that we obtain from the 3D prediction should match the image that we are observing from a novel viewpoint. So again, this is just a very standard view rendering loss that we can use to train this network, both while penalizing both colors and masks. And importantly, on synthetic data, we precisely know the cameras associated with each of these images because we are rendering them, and we have this multi-view data, and we can very easily sort of pre-train this gray network that I'm showing here across 40,000 instances from different categories. Now, so the more interestingly, once we have this initial network that is pre-trained on synthetic data, we can then just adapt it to better represent a new category that it's seen. Perhaps we are now interested in obtaining a 3D reconstruction model for the category of birds, and we can just fine-tune this gray network that we're seeing there to be able to represent birds. And the way we do that is again by using a rendering loss. So we say that given this one image of, in this case, a bus, our network predicts a 3D representation, and this 3D representation, when rendered, should match the input image. Now, unfortunately, we don't have the cameras associated with this image on the left. We only have the segmentation mask, and we don't know where this image is taken from with respect to some canonical ShapeNet frame. And to get around that, we essentially use this sort of a multi-hypothesis camera, where instead of having a single camera associated or predicted for each image, we have this multi-hypothesis camera where we are saying that for this particular instance, we believe the camera viewpoint is pi1 with probability rho1, it's pi2 with probability rho2, and so on. And we minimize the expected loss, and we are simultaneously training this category level network and optimizing the per instance cameras. And so we do this for a few iterations, and then at the end of the day can learn this blue network, which is category specific for buses. And just to highlight the training process for you, so given these two input images, these are the initial predictions that this pre-trained model gives us. And we're also showing 5 samples from sort of the 10 camera hypotheses that we initialized for this instance. And because it's an initial phase, all of them are equally likely with some probability, in this case, sort of 0.2. But as we...
So Shubham, maybe a quick question.
Yeah, sure.
How do you get this initial point cloud?
So this is the prediction of the gray network that has seen a lot of synthetic data.
I see. Okay.
So I think the main point to note is that this initial prediction is not very accurate, but it's something that's not very terrible and lets us get around, basically get around a lot of symmetries and ambiguities in this camera optimization.
Okay.
But of course, as we fine tune, both the shape becomes better and the cameras become more accurate. For instance, for the car, you will see that the camera that's looking at it, from the right viewpoint is just bright red. For the waist, something more interesting happens, which is it's a symmetric object, and there are still some ambiguities, and that's reflected in the camera distribution, where no single camera is peaky, but we have something like a more symmetric distribution because we don't precisely know which was the correct camera viewpoint. But again, as we mentioned, this initialization helps us avoid degenerate solutions. And compared to prior work where no such initialization was available, they would typically rely on these templates or some other sort of slightly hacky ways of getting camera initialization. Our work, by relying on this gray pre-trained model on lots of synthetic categories, can just get away from these assumptions and very easily fine-tune on new categories, given just segmented image collections and sort of no other requirements. And that allows us to train these category level experts across a very wide set of categories. In our paper, we sort of train these category level experts on around 150 categories. And then we can essentially distill them back into a common model that we are seeing on the left. So given just one image of, let's say, a laptop, we ensure that the prediction that our unified blue model is making should agree with sort of the pointwise density and color estimates that a corresponding category level expert for laptop is giving. And similarly for airplanes, we ensure that the predictions that our blue model, the unified model, is making are as close as possible to the predictions that the green category level expert for airplanes will make. And while our previous training objectives required us to do this volume rendering per ray, this step is actually much easier because we can just sample arbitrary points and just enforce that the predicted color and density from our predictions matches the color and density from the category level expert. So this stage is actually just much more efficient and much faster, even though we are distilling sort of 150 of these models into a unified model. And so I think those are some details, but at a very high level, it's an extremely simple recipe for training this unified network that can handle many categories, which is one, if we pre-train on synthetic data, that can help us get sort of useful initializations when we are self-training on image collections. And as I'll show in a bit, even though the categories that we are self-training on might be very different from the synthetic categories, for example, things like animals, this pre-training is sufficient to avoid degenerate solutions and can let us self-train on these image collections even for generic categories. And once we have these category level experts, it helps to distill them back into a unified model, which we'll sort of look at the benefits of in a bit. And here are just some qualitative results before we go into some numbers. Given these 7 images shown on the left, the top row is showing predictions from a work we had in last CVPR. We were using these adversarial constraints and learning this category-specific network. And you can see that it's learning some structure, but the predictions aren't that good. In particular, things like, there are arbitrary high-frequency details, things like skates, etc., don't look very good. And these are the predictions that you would get from a model that is just trained on synthetic data. And, again, they capture some coarse structure, which is actually very useful for us as an initialization, but don't model the details that well, or often have a lot of high frequency detail, which is not desirable. And these are the predictions that our category specific networks give when fine-tuned on each of these categories. And this is the prediction that our final unified model is giving across all of these. I think the important thing to note is that our performance is comparable, if not better, than the category specific experts. And the results at the bottom are obtained by this one unified network that basically has no notion of categories. And these, of course, also reflect in the numbers, which I'll sort of skip. Well, actually, maybe one interesting detail that we evaluated on 2 data sets, where the Pascal 3D data set overlaps a lot with synthetic data. And, in fact, all of the categories that you're seeing on the left were also observed in ShapeNet. And so the synthetic data model actually does sort of a bit better than something like SSMP, which is only trained on this real data. And our improvements over the synthetic model are perhaps not as impressive. But if we also test this model on other categories, for instance, from the SCO 3D data set, where these categories are much more different from the synthetic data, we see that the improvements that we are getting by the self-training are much more significant, and that our final model is actually doing slightly sort of comparable and slightly better than the category-specific experts. But I think perhaps the most exciting result for me was that if we have this unified model that has just seen many categories, in particular something over 150 categories, it does a reasonable job at predicting 3D structure of just generic objects. So for instance, if we showed this, I'm not even sure what this is, perhaps sort of a Spider-Man shaped cake, it can infer some meaningful 3D structure. And similarly for this, again, I'm not sure, perhaps something like a scooter, or actually scooter with a bag hanging from it, can again predict some meaningful 3D structure. And we also sort of tried to quantify this, where from our final model, we actually just held out a few categories. So this is again overlapping with the previous table you saw, but in this case, the distillation model was not distilling the experts on these categories. So essentially, we just held out these categories from training. And then we saw that synthetic model, which has seen just something like 50 categories, gives us some error. And so in this table, sort of lower is better. And if we add more categories to it, in particular, we add something like 35 more categories to the synthetic model, the performance improves. And if we add 50 more categories, again, which are not overlapping with the categories on the left, the performance improves. And so this is a very encouraging result, just telling us that the more categories we see in training, the better our performance might become on just unseen categories that the model hasn't been trained on. And at the end of the day, we get this single unified model that can just take an image. And again, I apologize, these should really be segmented. That can just take an image with sort of the foreground mask of the object and predict the 3D structure of them across all of these objects that you're seeing here. I believe I might have some GIFs for this.
So Shubham, how sensitive are these reconstructions? Like, instead of using the ground truth segmentation, if you use predicted segmentation?
Yeah, so that's a good question. And actually, we were already using something like a predicted segmentation for a lot of categories. So I think the data sets that we used were sort of hybrid and collected from all over the place. So in particular, for all the animal results that you're seeing, there was even no ground truth segmentation on ImageNet. So we had to actually rely on models that were trained on COCO and then applied them to these ImageNet crops and just use those. For open images as well, the segmentations they're annotated, but they're not very precise. And so I would actually say that across most of the categories, the segmentations were actually not very good.
I see. So I guess if my intuition is correct, you're doing this reprojection loss, right, to refine your 3D model. So if like, a fraction of the pixels are off, then it should not really matter that much.
Yeah. So I think what makes the model fail, and this is something I'll get to in a bit, is if the object is just severely occluded or truncated. And in all of, as in I skipped this detail, but we actually trained this simple model where we gave it examples of, okay, this is a bad image, this is a good image. We gave it something like 3-4 examples per category. And then we used its predictions of truncated versus not truncated to filter out data.
I see.
So that I think is critical, but perhaps some approximate segmentation being off is fine.
Okay.
Yeah. And again, I think to reiterate what was interesting or cool for me about this project is at the end of the day, we get this single model that you can just download and give it sort of any segmented image, and it can do sort of a not so terrible job at reconstructing any object that it's seeing. I think most of the results here are within sort of the 150 categories that we trained it on, but it is such a broad set of categories that its predictions are typically meaningful across a wide range of objects. And sort of, I'm just showing you a few more. In particular, I think we have a demo which you should be able to just download and try. So this is just me running the demo on some specific image of this car, and within a few seconds you get this extracted mesh out. And hopefully, if you are interested in trying this out, it's just as simple as loading a model and giving it a new input image and a new segmentation mask, which I think I might be trying to do for a dog in this case. But again, yeah, I would encourage you to check out the demo and the code that we've already released for this. But actually, sort of going back to a question that Pulkit was asking, that one fundamental assumption that we were making that I didn't at least mention initially was that we are assuming that the object is unoccluded. We are saying that the 3D structure that we predict should render, so the full rendering of the 3D structure should match all of the pixels in the foreground. And if, for example, this bus was occluded by perhaps another bus, the training process would really fail because the 3D structure that is rendered would not really match the pixels that we are seeing. Perhaps the foreground mask would be misaligned, perhaps the color values would be misaligned, and so on. And because of this, the model that we have finally cannot really handle occlusions. All of the results that you are seeing were across these fully visible objects, and our model is not applicable to settings where you're only observing a small number of pixels for a particular instance. But of course, that is a very practically relevant setting. For example, if you're seeing a dining table, you're not likely to observe all pixels of the chair that's behind it, and you would still want to be able to understand the 3D structure of what you're seeing and perhaps be able to infer the 3D structure, something like what's shown here. And in this task, I'll not be able to talk about how we can make steps towards this and sort of just handle generic occluders. But one very specific occluder that I think is a sort of interesting special case is that of hands. So, from when you wake up in your morning, you are interacting with different objects using your hands. You shut off the alarm, actually, or these days just tell Google to shut up, or sort of brush your teeth, open drawers, drink coffee, and so on. And so throughout your day, your hands are interacting with objects, and being able to understand these interactions in 3D is, of course, very useful for, let's say, a robot that's trying to understand your demonstrations, or is very useful for a virtual assistant that's, again, trying to understand what it is that you are trying to accomplish and might remember what you did, or perhaps might assist you and give you instructions later on. And so in this particular case, again, often your hands are significantly occluding the object that you're interacting with. For example, this particular pencil or the toothbrush or some pixels of the coffee cup are being occluded by this manipulator that's interacting with them. But being able to understand the 3D structure of the object in hand in this special case is, of course, a very interesting and a challenging problem. And before going into details of our specific work, I do want to acknowledge that there's, again, a long history of people looking at humans or hands interacting with objects and being able to understand that. And I think there's been this very clear trend of shifting from recognition-like understanding, where given just a video, we wanted to sort of label that this is an activity of skiing or this is an activity of sort of bull riding, to something that is more spatially grounded. And in particular, some recent works have looked at 2D spatial grounding, where, say, we are watching a video of a hand or an image of a hand interacting with an object and can label the bounding boxes, etc. And more relevant to us, I think there's also been some growing interest in being able to just understand the 3D structure of the objects. In particular, let's say, given this video of a hand interacting with a light bulb, being able to understand what is happening from a more geometric perspective. And while the two videos that I'm showing here look very impressive, and in fact, all of the papers cited here would give you something like these outputs, one fundamental assumption that most of these approaches are making is that they know a template of the object that is being interacted with. For instance, if you're holding a cup, a user would select that you're interacting with an object that looks something like this. And so given this additional information, the task is reduced from something like 3D reconstruction to almost a 6D pose estimation, because we're just given this approximate shape of the object already known. We're just interested in situating it in context of the camera frame. And there are a couple of challenges or limitations of this assumption. One, of course, being that having this small set of templates, as we saw earlier for 3D annotation, is not sufficient to capture a lot of variation. But sort of also more fundamentally, it requires a human in the loop for every new image or video that you're interested in, where the human is annotating which specific template was being used. And this makes it not very applicable to generic objects, and also limits how easily. And so I want to give you sort of a very brief overview of one work that we did, which again had this goal of, given an image, being able to reconstruct the hand and the object that is being interacted with, but do so given just a single RGB image and not make any additional assumptions that, let's say, the approximate template model of the corresponding object is a priori known given the video or given the image. And the reason why we were able to do this task, which at the surface seems like a very hard one, is that hands are a very special occluder. In particular, if you see a hand having a grip or sort of having an articulation that is shown on the right, you know that more often than not, the hand is interacting with a very thin object, perhaps grasped in a specific way. And given this articulation, you would know that it's something like a pen and probably not something like a plate that you're holding. And this on its own is not sufficient. Sort of as a complementary fact, we have made sort of very impressive progress in being able to understand the structure of hand given images, even occluded settings, and off-the-shelf hand pose estimation is actually pretty reliable. And being able to combine these two insights, that the pose of the hand gives us cues about the object, and that we can reliably infer the pose of the hand across a lot of scenarios, helps us tackle this task of reconstructing generic objects and hands, just because of the special structure of this problem. And
so Shubham, when you say this is very reliable, is this very reliable even on YouTube videos? If you go, the hand pose will work quite well, or is it reliable maybe on Flickr style images?
So I think so these are visualizations that I'm showing here on David Fowey's 100-day hand data set, which is sourced from YouTube. So I think maybe I should put it this way, that it's pretty easy to get frames where it's working very well.
Okay.
If you look at a video and you're expecting it to be very smooth and consistent, I don't think it's quite there yet, especially because these systems were actually per frame. But if you're looking at a lot of frames of this, I'd say maybe 70-80% of them you might be okay with.
I see. Okay. Thank you.
Yeah. And so for this task of being able to infer 3D from a single image, we actually just operationalize both these assumptions, which is one, we use some off-the-shelf predictions to estimate an initial or estimate the hand pose. And then conditioned on this estimated hand pose, we have this articulation-aware 3D prediction network that really takes into account how the hand is structured and reconstructs the object in context of that. And I think sort of one very important detail is that in this figure, you are seeing the 3D reconstruction in the image frame, which is, we have put the 3D model of the object aligned with the image pixels, but sort of a frame that is much easier to reason about the object structure is this frame centered around the hand wrist. And so I think this is just a video showing our per frame predictions on this specific object, where you see that the image frame predictions vary a lot, but in context of the normalized hand frame, the prediction task is much easier. And things like articulation, condition, shape prediction is much more informative in context of the hand frame. Because again, if you're holding a pencil, no matter how your hand is moving in the image, your prediction might be very similar in this normalized hand frame. And instead of trying to predict 3D directly in the hand image frame, we predict it in this normalized hand frame, which again, because of predictions from off-the-shelf systems, we have some notion of how the hand frame is associated with the image frame and what the articulation of the hand is. And sort of in particular, we reconstruct the 3D structure of the object in context of the hand and then place it back in the image to generate the visualizations that you're seeing. And okay, I might sort of skip most of the details to sort of leave a few minutes for discussion and maybe just give a couple of comments on the overall architecture, which actually is just an extremely simple architecture. So it uses an implicit network. So given a particular query point X, which is in the context of the hand, we want to infer its sign distance function, which can let us represent the geometry using this implicit representation. And to output this sign distance function for this point X, we combine two features. One is a pixel aligned feature. So given this point X, we project it back to the image and extract some visual features. And more importantly, we look at this point X in context of the articulated hand and have this sort of articulation-aware position encoding, which you should look at the paper for, and concatenate both of these and pass them to a very simple network that outputs a prediction for the sign distance function for this point X. And we sort of test our approach across three data sets. Sort of the left one is synthetic and has a lot more diversity, and the two on the right. So the middle one has much less diversity in terms of objects, but many more images. And the one on the right has more diversity in terms of objects, but very small number of images. And again, I might skip most of the details. I think one possibly useful, actually, perhaps I should have had a better example for this, but at a high level, we do see that articulation is important. For example, given this synthetic image that you're seeing on the left, the particular articulation of the hand, the fingers are curling back in the front. And so the shape that is predicted in the middle column is not very plausible given this articulation. But if we are not reasoning about articulation and only reasoning about image pixels, this is something that projects well back to the image. whereas our prediction, which is accounting for this articulation, is perhaps a bit more natural. And again, I think I'll skip some of the details here and comparisons to base. I think, yeah, one additional property of our system is that it's relatively robust to prediction error. So this is F score on the y-axis. So higher the F score, the better the prediction is. And here is our result compared to the baselines. And in this figure, our system is using off-the-shelf prediction from a system called Frank mocap. And the prediction actually improves by a reasonable amount if you use the ground truth prediction, sorry, the ground truth hand pose. But more interestingly, if we are using pose that is twice as inaccurate, so we take the ground truth pose, we take our predicted pose, and make our predicted pose even worse by extrapolating away from it. And that gives us this line that you're seeing. Actually, perhaps should have labeled it. Sorry, something broke. Yeah, so the line that you're seeing on the left for ours is one where we extrapolate the prediction error to be twice as much, and we are still significantly better compared to some of the previous baselines. And one sort of additional thing that you get for free is, given the sign distance representation, it's very easy to reason about contact. And just as a post-processing, we show that if we have the sign distance function-based representation of the object, we can actually refine the hand pose to encourage contact with the surface a bit more, and that slightly improves the hand pose and makes sort of contact, etc., much nicer if that is something that's relevant for the application load stream. But again, all of these results are without this additional processing, and given just this single image, we are able to reconstruct plausibly the structure of, at least the core structure of the object being interacted with, given just the single image. And again, I would like to emphasize that this prediction in context of the hand space makes a lot of sense. For instance, if I'm holding or touching a chair, we don't want to frame the task as reconstruct the entire chair, but we only want to phrase the task as reconstruct some local structure in context of what the hand is touching. And this approach is one plausible way of getting this 3D representation in a hand-centric coordinate. And yeah, I think with that, I want to open for any questions and just remind that towards this goal of being able to reconstruct generic objects in the single view setting, I showed a couple of steps. One that let us scale to more generic categories, and second that let us get around occlusions, but for this very specific occluder of hands. I'm happy to take any questions.
Well, let's thank Shubham for the talk. And now we can open for questions.
I have a question. Hi, Shubham. Talk. So my first question is just to get like a high level understanding, because like the first project, the architecture or like the Pygan thing, or maybe I forget the name, but it looks quite similar to NERF. But I guess the main difference that makes it able to do this single image inference is the fact that you're conditioning on an image now, and you've also have a large pre-trained data set that basically gives you like a 3D object prior, right?
I mean, so from the perspective of the network, it's just the former, right? That this, instead of having a NERF which sort of ignores the Z and only answers queries for a particular X, there is this Z which is predicted in an image conditioned way that can let you handle diverse shapes.
I see. Okay, and then I had so one other question was, so you said that the hand pose estimation right now, when you have like a video, it can usually give you a few good annotations out of like a video of many frames, like a few will be very right. So I'm curious.
More than a few. I would say the majority would be approximately good.
Oh, I see. But I guess what I was going to ask is it easy to get like a measure of like how confident you are in your predictions out of these models, and has there been work in trying to like smooth out the predictions by like taking the most confident predictions and using that to like correct the
yeah, that's a good point. And I'm not super familiar with some of these video-based hand prediction approaches yet. I don't have a very good answer for this. I'm not sure. Sorry.
Okay, no problem. Thank you.
As in most work that I'm aware of, just does look at single frame. That's what we've been using.
So Shubham, the results that you have with object reconstruction with the hand seem really good. So in the first part, right, we were assuming segmentation, and that was helping us do the reprojection.
Yeah.
So are we also assuming segmentation over here?
Oh, sorry. Okay, I should have been more clear on this, but I think all the data sets that we used in this case had. Where did the data sets go? So all three data sets that we used did have either ground truth or approximate annotations for the objects, which is something we were relying on. And so you would note that the diversity of objects that we are seeing here is not very high. It's some very, as in all of these things like bottles or planar structures or bananas, etc. It's not a system that works for out of distribution objects yet. So if I sort of take my AirPod and hold it, or take my laptop charger and hold it, I don't think it would work very well.
I see. So, but for these videos, were you assuming there was some segmentation annotation on these videos also, or these videos were out of domain, I presume, or no?
So do you mean during training or during inference?
During inference.
I see. So actually during inference, we're just doing a per frame inference, and we're not assuming anything that there's segmentation. But during training, we're assuming ground truth 3D, so that simplifies the task a lot.
I see. So at test time, it is.
So at test time, it's just this one image, and we are predicting whatever you're seeing there, and no additional segmentation.
I see. Okay, cool. Any other questions from anyone?
Right, I guess I had a question. I was wondering, do you have any results or on how this method would work on a video of data? I know you said you mostly do single frame, but just if you just run it on every frame in a video and overlay the result on top, how much stability do you see?
I think the one video I showed was perhaps the best case of it earlier, where we were seeing these normalized hand frame. But I think the typical videos are much worse, and actually that's something we are looking at, which is if you see a video, then you know that there's this one rigid object, at least in most of the cases, which is perhaps rotating and moving in your hand, and so can we do a better job at being able to reconstruct it? And I think our system is not yet very good. I think, again, this is perhaps the best case scenario, and for generic objects, there is a lot of jitter and structure change across frames, which is not great. But if you look at them in isolation, each of them might seem not too bad, but they are bad, slightly bad in very different ways in different frames, which makes it not very nice.
So what do you think is the biggest challenge in making this, consistent across frames? Is it that we don't have good video processing architectures? Is it,
No, I mean, I think I don't think there's a very big challenge. I feel within a year or so, we might have methods that do a good job. So from a technical perspective, the object themselves might move in hand, and that is something you need to reason about.
Okay. Great. So, I think we are coming to the end of the talk. So it's almost noon. So let's thank Shubham once again for the wonderful talk. So Shubham, these videos look very exciting. So, really hoping to see how they look like in the wild in some time. And I guess, Shubham, you have your schedule, right? So there's some meetings, maybe with a couple of people.
Yeah.
Okay.